Hello, Assalamu alaikum students. So let's see the relevant theory for the hydrostatic force experiment. So the title is to determine the hydrostatic force on a submerged plane perpendicular to free surface of water and to determine the location of center of pressure. So we have a submerged plane perpendicular to free surface of water. So this means we have a vertically submerged plane and we have to experimentally determine the hydrostatic force and locate the center of pressure. And then later on we are going to compare it with the theoretical computations. So apparatus which we require consists of this hydrostatic force apparatus, which has this transparent water tank to store the water, and we have this quarter part of a donut which is called a toroid, and we have this vertical surface. The pressure, the hydrostatic pressure will be exerted on this vertical surface or vertical face of this toroid. The apparatus is provided with a rod or a beam, you can say, which is supported at this pivot point, which is called fulcrum. Fulcrum is a point of rotation of this beam. On one end we have this counterweight, and on the other end we have this weighing pan on which weight is placed. It is also provided with a bubble which enables us to balance it, and we have this hook gauge to know the water depth, which is provided with this scale. So let's quickly see some relevant theory. The hydrostatic force is a force which is exerted by the static water on a plane or a curved surface, and it always acts normal to the surface. Theoretically, hydrostatic force, it is computed by this formula gamma AHC, where gamma is the specific weight of the fluid, which is also written as rho g. Area is the cross-sectional area of that object or the submerged surface, and HC is the distance from the water surface to the centroid, or you can say center of gravity or center of the object or surface. Previously we have used the formula H dash to represent it. You can use either H dash or HC. Then we have toroid, which is a quarter piece of a spherical disc or a donut, which is connected to the arm. Only at one plane of the toroid force is experienced. Point gauge or hook gauge is a measuring device used in this apparatus, which is used to measure the water level and to find the depth of water. A scale is calibrated on it. Bubble level is used to perfectly balance the hydrostatic force apparatus, and the point of application of hydrostatic force is called center of pressure, P, and the depth of this center of pressure is HP, which can be computed using this formula. HP is HC plus IG over HCA, where HC is the distance from the water surface to the centroid of the vertically submerged surface. Ig is the moment of inertia about its centroidal axis, and the area is a cross-sectional area. So it basically depends upon the geometrical properties. So it has two cases. Case 1 is for partially submerged surface when d1 is less than d. So d1 is the distance from this bottom of toroid to this water surface, and d is the thickness of this toroid, or you can say the height of this vertical surface. So this is a schematic diagram where this is the water tank, and this line represents the rod, and on one side of this rod we have a counterweight. It is provided with a bubble level, and this is the pivot point, or you can say fulcrum or point of rotation for this rod, and on the other end we have this weight pan on which weight is placed, and its distance from the center of this weight pan to this pivot point is Z. And this is a toroid, which is a quarter part of a donut, you can say, and the distance from this pivot point, or you can say radius of curvature for the inner part is R1 and for the outer it is R2. So R2 minus R1 will basically give us the thickness of this toroid or the height of this vertical surface. And only this much part of the toroid which is inside the water, it is going to experience the hydrostatic force. So quickly see some symbols. So D1 is the depth of water from the bottom face of toroid. D is the height of plane surface, the thickness of the toroid you can say. R is the radius of curvature of the quadrant. B is the width of plane section facing water. Let me show you this figure as well. So if I draw this side over here, and if I show you the cross-section shape, so its width is B and its height is D. And this dashed line, this represents the water surface, and the distance of the part which is in water, it is D1, and the distance till the point of application of this hydrostatic force, it is HP, and HC is the distance till the centroid of this submerged part from the water surface, and FH is the horizontal thrust. Theoretically, we can determine the hydrostatic force using the formula where HC will be till the centroid of this submerged part, and for a rectangle we know it is half the height, so it will be D1 by 2, and the area will be for the submerged part, so it will be B into D1. So theoretically it will be gamma B D1 square by 2. And the center of pressure, it can be computed using the formula, or you can simply use the pressure distribution, and that it will be the centroid of a triangular surface, it is 2 by 3 D, so the submerged height is D1, so it will be 2 by 3 D1. For the experimental force, we have to balance the disturbing torque with the resisting torque. So this weight which is acting vertically downward, it is going to disturb this beam which is balanced by this hydrostatic force. So we have to take moment of both about this pivot point, and as you can see, this weight is going to produce a clockwise moment, while this hydrostatic force is going to produce a counterclockwise moment. So they are balancing. So the disturbing torque is W into the lever arm till its pivot, which is Z. So WZ is equal to this hydrostatic force into its lever arm, which will be R2 minus D1. So by that I have reached the water surface plus HP, and HP is 2D1 by 3. So we'll get R2 minus D1 by 3. So we can rearrange this expression and get it for FH experimental, which will be W into Z divided by R2 minus D1 by 3. So let's see the second case for a fully submerged surface when D1 is greater than D, that is the water depth is greater than the depth of that section. So hydrostatic force will be experienced by this vertical face of this toroid by the horizontal hydrostatic force FH, and a vertical hydrostatic force will be experienced by this curved part of this toroid. So as we have this fully submerged surface, so water depth is given by D1, and this is the hydrostatic force FH which is acting at HP, and this vertical part FV, this acts at a distance x from the center, As we know, for a quarter, its centroid is at 4r/3 pi. So this Fe will act at this x distance, and this r, it can be computed as d1 minus d. So let's see the theoretical formula. HC, now this will be the distance. So centroid of this complete part, it will be at d by 2 from the bottom. So HC will be d1 minus d by 2, and the area will only be the area of this complete submerged part, so it is B into D. So theoretical formula, FH will be gamma BD into D1 minus D by 2. And for the depth of center of pressure, using the same formula, just substitute all the values. This is for the HC, and IG will be BD cube over 12, and simply rearrange it, you will get it in this form. And for the experimental force, we have to balance the disturbing torque and a resisting torque. And in this case, this weight, it is producing a clockwise moment, as well as this vertical force, this is also producing a clockwise moment. So it will be in the disturbing torque. So W into Z plus FV into X is F experimental into the lever arm, which is same, R2 minus D1 plus HP. Just rearrange it and you will get it in this form. So let's quickly see the procedure, the steps involved in performing the experiment. So first of all, the rod is balanced by using adjustable weight until the bubble of the level comes in the center. Then fill the tank with water, just touching the lower surface of the toroid. Then the depth is found out by moving down the pointer needle until it touches the water surface. And at this point, you're going to set that hook gauge to 0, 0. This will be the reference point. And then put some weight on the weighing pan, and it will cause the rod to be disturbed. And we're going to balance it by adding some water to it. And you have to note the position of the bubble. Once it comes to the center, it has been balanced. And you have to take 3 readings for a partially submerged case and 3 readings for a fully submerged case. And note down all the perimeters required. The procedure is repeated and more observations are taken, and a table is constructed and graph is plotted between F theoretical on the x-axis and F experimental on the y-axis. So let's see the observation and calculation table. So some of the data related to the apparatus is already provided here. The outer radius R2 is 8 inches, and the moment arm for weight, that is Z, is 30 centimeter. The width of the section is 3 inches and the depth is 4 inches, and D1 is the depth of water, which is variable. You must also watch the video by the name Hydrostatic Apparatus Performance on the YouTube channel and note down all the observations and then carry out calculations on this table. The mass in grams and the depth D1 in millimeters, these were the 2 observations taken, and you can fill out the remaining components using the formulas discussed. And you have to compare the theoretical values and experimental values of the force, and the center of pressure will only be determined theoretically. You can plot a graph using experimental value of force on the vertical axis and theoretical value on the horizontal axis, and then draw the best fit curve. So that's it. Thank you so much.